Okay, first of all, also I would like to thank the organizers for inviting me. Also for giving me the title of professor, which I'm not. I'm still a doctor, but anyhow. I'm presenting this work also on behalf of Dr. Petra Mens, who is leading our malaria research group in our institute. Very brief introduction. We focus mainly on research on malaria, leishmaniasis, cryptosporidiosis, and soil-transmitted helminths. And our main focus is development, evaluation, and implementation of new diagnostic tests for these diseases, but also combine that with monitoring and improvement of treatment in efficacies on disease epidemiology. And we hope to contribute to control programs by doing this. And of course, knowledge transfer and capacity building is quite essential for us. So we work in many African settings like Burkina Faso, the Gambia, Benin, Nigeria, Kenya, Rwanda, Sudan, Ethiopia, but also in Latin America, in Suriname, one of our previous colonies, and Thailand. And we do take up a lot of PhD students from those countries to also build capacity over there. So today I will be talking mainly about malaria and about undifferentiated fevers. And I think there's a lot of good news to tell nowadays about malaria. In the past we used to see that every fever in sub-Saharan Africa was treated more or less as a malaria infection. Nowadays that has shifted. We have now really test and treat strategies in place. And mortality and morbidity of the disease is really going down, and the E word is buzzing around. So really countries are thinking about malaria eradication and elimination. Also in countries in the developed world, we see a strong reduction of import malaria. For example, in the Netherlands, a decade ago, we saw about 500 to 600 import malaria cases every year, but still 5 to 10 people dying. And that is now also being brought back to marginal around 150 cases per year and no deaths. And we have effective artemisinin-based combination therapy in our hands that can really help us to battle against malaria. Of course, there is also the downside. There's still some points of attention. That is, of course, drug resistance. And we have seen that in the past, chloroquine and fansidar have been lost as effective drugs. And there are nowadays, and also highlighted yesterday by Colin Sutherland, some reports from Southeast Asia, and also possibly from Africa, that there is at least a decline in efficacy of the ACTs. If it's really resistant, that's a thing that really has to be sorted out. But also we see that other important risk groups are emerging. For example, pregnant women. That is a group that has been overlooked, let's say, in the last decades. And we now are realizing more and more that malaria has this very huge impact on the health of both mothers and also their children. And also we see a lot of migrating populations, not only within Africa, but also from Africa to Europe. And those people are also having a lot of problems with management of malaria. Now, the diagnostic tools that we are currently using for malaria have been quite effective so far. Microscopy, and since the last 20 years, rapid diagnostic tests have been are being widely used, and they have relative good sensitivities in for microscopy. For the rapid diagnostic tests, it is less. The rapid diagnostic tests do have the advantage that virtually everybody can do that, whereas for microscopy you really need some training and well-maintained equipment. Microscopy has the big advantage that you can do species identification and you can actually quantify the number of parasites, whereas quantification is of course not possible with the rapid diagnostic test. And species identification, there are a couple of RDTs available that give the ability to do some species identification, but often these have limited sensitivity. And of course, the quality of microscopy really depends on the microscope and the training of the microscopist, and it is really a bit of a dying art. not only in the Western world, but also in Africa, because a lot of people are nowadays relying on these rapid diagnostic tests, of which many brands are available with a huge variation in quality difference. So we think that there are still, there's a rationale to develop some new tools for malaria, and especially in areas with declining prevalence, for elimination groups, but also to detect parasites in more vulnerable groups, like the pregnant women. Studies in our group have showed that both microscopy as well as rapid diagnostic tests are really missing a lot of infections in pregnant women. And of course, we want to detect all resistant parasites in order to be able to contain emerging resistance. We, in our group, work really hard towards developing and implementing molecular diagnostic tests for all kinds of parasitic diseases. But of course, these platforms are often incompatible with near point-of-care diagnosis. They require DNA isolation. There's the contamination risk, so that you have a lot of false positive results. Sometimes difficult readout systems, the shell systems that you maybe needed to get your result. It requires quite some investment in training of staff. A cold chain is needed to preserve particularly the reaction enzymes and the primers that go with it. And of course, there is the issue of equipment. Now, what we have taken as approach is the so-called direct-on-blood PCR NALVIA system. As said, it's direct on blood, so it does not require DNA isolation or processing. It has short multiplex amplification protocols. It uses NALVIA, nucleic acid lateral flow immunoassays, as a readout system. These are a kind of tests that are comparable to the lateral flow test that we see in rapid diagnostic tests. We have developed a closed system. So once the PCR reaction has taken place in the tube, there is no need to open the tube and do all kinds of pipetting. So that should dramatically reduce the risk of contamination. And we are working towards stabilization of the PCR reagents by lyophilization. So this is the principle of the direct blood PCR. So you have a finger prick. It goes into the tube. The tube has the stabilized PCR reaction. You do the PCR assay. That can be, of course, in a sophisticated PCR machine, but also these small handheld PCR devices. This is the palm device. You can use to do the PCR, or you can use battery or solar-powered operated PCR machines. And then the amplicons, so the tube is now in this green holder, are directly placed on the lateral flow device, and you can read that out. This is the NALVIA principle. So we are using a nitrocellulose membrane, on which, in this case, two types of different antibodies are being spotted, so anti-tex red antibodies or anti-Dig antibodies. And during the amplification process, by using specifically labeled primers, you will build in either text address or Dig labeled PCR fragments. And on the other hand, you can have carbon labeled parts that are used for visualization of the product. So in this case, we have developed a panplasmodium test, so that is detecting all 5 human species, of maybe even all 6 human species of plasmodium, and GAPDH as an internal amplification control. So after amplification, you will get and transfer of your products to the NALVIA stick. You can have, so we have the control line and the panplasmodium line. And if you go to, let's say, this one, so we have a test line and a control line. So that's a plasmodium positive sample. And in the case of a plasmodium negative sample, we will only see the control line. This is a water control test failure, so neither the test line or the control line is visible. And here we only see the test line, but not the control line. So this is also an inconclusive test or a test failure. It's a black and white reading, so it has a very good visibility. It's very easy to read out, and it is, I mean, there's not much training required to do the reading of these sticks. We have this Panplasmodium nalvia test has been extensively tested in a variety of laboratories. First of all, in our own lab, we have found that it has a detection of an analytical sensitivity of around 1 parasite per microliter of blood, and the sensitivity and specificity of 98 and 99% respectively. Subsequently, we have performed a ring trial in which 3 independent laboratories in Europe with PCR expertise were performing our test. They were giving no training, but only the SOPs and the tests to run. And they've reported comparable sensitivities and specificities of the test. So the next step was to bring these tests to the field, and we have tested them in Kenya, Burkina Faso, and in Thailand. Thailand as being an environment rich of Plasmodium vivax. And again, comparable range of sensitivities and specificities were found. And all the operators reported the ease of use of this system. So we are now moving this test forward thanks to funding by the European Union. We have a project called DIACMO, and we are now working towards a multi-analyte system. Our work in Thailand showed that there were some problems with P5X detection, in particular at the low level of infection, so around 2 parasites per microliter. So we are at the moment still working to increase this. And the test now has 4 different lines. So there's a Panplasmodium line, a Plasmodium falciparum line, a P5X line, and again this internal amplification line. And so is it looking after you have done your test? On top we have the Panplasmodium positive one, so we see one test line and one control line. But in the case of Plasmodium vivax, we see that 2 different test lines are occurring next to the control line. And with a Plasmodium positive signal, we see again a test line, a second test line, and the control line. And with mixed infections, we see 4 different lines appearing on our nalvia stick. So this is a Plasmodium negative sample, only the control line is visible. And again, this is a water control. At present, the analytical sensitivity of the limit of detection that we have achieved in this multiplex system is for plant Plasmodium around 1 parasite per microliter. For falciparum also, again, 1 parasite per microliter. Vivax, it's somewhere between 1 and 5 parasites per microliter, and for mixed infections, also 1 to 5 parasites per microliter. Probably somewhere in the multiplexing of the system, you are losing some of your analytical sensitivity, but we are still trying to improve this so that for all the 4 lines we will have this low sensitivity of 1 parasite per microliter. We already have been able to do some analytical accuracy studies by using negative controls from the Dutch blood bank and positive patient samples that were donated by Colin Sutherland from the London School. And again, we see that there is a very good sensitivity of 100% and the specificity of 98%. That was due to the fact that 1 negative sample was found positive with Plasmodium falciparum. So if you think, is the direct on-blood PCR nalvia system now really an add-on to that what we have? I think it is. One of the big advantages, if you compare it to other available technologies like standard PCR platforms, real-time PCR, but also NASBA. We, in the past, have been working a lot on NASBA technology because of its isothermal characteristics and LAMP. Then for sure, this direct-on-blood PCR NALVIA system has the advantage that DNA isolation is not required. Both NASBA and LAMP claim to be isothermal reactions, but still for NASBA it is done at 2 different temperatures. And LAMP also has some problems with, let's say, multiplexing of the system. We have a closed system. We are able, in contrast to some other technologies, to do species differentiation. We do have an internal amplification control, and the system has a very simple readout system. And results are available within 1 hour, and you can run several tests at one time. So you can really use it as a kind of a high throughput system. So within this DIACMAL project, we are really trying to develop a ready-to-market project. We have a consortium with some small, medium-sized enterprises are represented that will take care of CE marking and marketing. We are in discussion with WHO whether or not we can go for pre-qualification. WHO has this pre-qualification scheme for rapid diagnostic tests. And we are discussing with them whether or not we could also go for a molecular diagnostic test that can go for pre-qualification. And this year we will do further field evaluations in Kenya and Vietnam. And what we really want to do, of course, is integrate our system in other research projects for which we are currently seeking funding in elimination settings and malaria in pregnancy studies. What we are also thinking of is, of course, NALVIA. It's a nice system, but it is really targeting one disease. And we really would like to go to a syndromatic approach. So that means we want to go from NALVIA to NALMIA. Now, NALMIA stands for nucleic acid lateral flow microimmunoassay. And that's a multi-analyte system that has up to 25 spots, or targets, or different diseases. And again, if you run this system, then you have your results available within 10 to 15 minutes. It requires also multiplex amplification. We want to do it direct on a clinical specimen, so that can be blood, but we are also thinking about nasal swabs and stool samples. And if you, we want also to couple this system to the dedicated reader system that can capture the image, give you the result, and also helps you to store this information in surveillance systems. And why do we want to do it? Well, of course, what I said in the beginning, that fever does not longer equal malaria. So there's a lot of undifferentiated fevers. But we see, for example, in Burkina Faso, that outside the rainy seasons, we still have a lot of children that have fever. These children do not have malaria, but they do have something else that needs to be treated. But also in Europe, we see that there is a re-emergence of all kinds of vector-borne diseases. There have been outbreaks of dengue and chikungunya in the south of Europe. There was a 5-ox outbreak of malaria, of Plasmodium 5-ox malaria in Greece. And we have a lot of returning travelers with all kinds of fever, caused by Hanta, leptospirosis, and typhoid fever. And all those need to be diagnosed well. And there's an inherent risk that you don't perform appropriate treatment, maybe too late, too much, or too little. And there's a huge risk of developing resistance, in particular antibiotic resistance. So our NALMIA platform is a highly flexible generic platform. So you can adapt it to epidemiological needs. And that is due to the fact that these discriminative tags allow for building a flexible platform, and then you can make platform, for example, for a returning traveler that may have malaria, typhoid fever, leptospirosis, or for a child with fever that has a pneumococcal infection or infection or a staphylococcus infection. Or you can address outbreaks in southern Europe, what we have recently seen with West Nile virus, chikungunya, dengue. And so you really would like to have, but that's really for the future, a test, in this case for vector-borne diseases. The patient is diagnosed with a NALMIA test. The results are put in the cloud, fed into surveillance systems, and that can help early warning and response systems. So the last thing that I wanted to touch upon, but I think we are limited on time, so I will just briefly mention that it's also a research that we have really initiated during the last couple of years, that is to develop molecular tests that can aid detection of drug resistance markers. I think drug resistance has already been quite extensively addressed the last couple of talks. We know that drug resistance is often confirmed by by mutations in genes of the parasite. PCR RFLP is, let's say, together with sequencing, the most frequently used technologies to detect these resistance markers. But we have adopted multiplex ligation-dependent probe amplification in our lab. It's a technology that was introduced by Richard Anthony, who will also speak today of our TB group in our institute. And primary extension combined to NALVIA, that was being developed within the framework of our Malactrus project by Aart van Amerongen from Wageningen University, and again by Colin Sutherland from the London School. Yeah, these technologies are quite promising. I will not go into details, but for example, if for MLPA analysis, you can really address quite a lot of different markers in one go. Here we have tested some different standard falciparum strains for their drug resistance profile, and it gives you a nice print of the markers that are there for resistance. And also with primary extension, where depending on whether or not a mutation is present, a PCR product will be formed. And this PCR product, in analogy to the malaria diagnostics, can then be visualized on a NALVIA stick, where you can also get these nice lines that can discriminate between the wild type and the mutant. And these are also promising technologies that we want to take up in the coming years for drug resistance next to our work on diagnostics. Finally, I would like to thank all our collaborators, but in particular all patients, research staff, parents and volunteers who participated in our studies. Thank you very much.